All right, so first off for 5.2, it's just introduction into rate law. And what a rate law looks like, and they'll ask you to do this on the AP test often, is they literally want you to write the word rate. So if it says what is the rate law as the question on the AP exam, you have to actually write the word RATE equals. And then after that, you're going to put this lowercase k, and that's a rate constant. We'll talk about that today a lot. We're going to find it with this problem. Then you use the concentration of the reactants to some power, and you can use A, B, C, X, Y, Z, it doesn't matter. So inside the bracket is a reactant for your reaction. And if there's a second reactant, you would put another one and then another power, and again, X, Y, Z, A, B, C, N, and M. Just as long as they're letters, you'll be fine. All right, so for the reaction that we're going to do on page 640 to 641, those are our two reactants. So I'm going to write down that one of them is this nitrogen dioxide, and then the other reactant is carbon monoxide. And the hope is to find the X and the Y and the K. So what you're going to find here is it's not what you think. A lot of people think you're going to find the rate word, but you're actually not. You're actually going to find or try to find or solve for what's X. You're going to try to solve and find for what's Y, and you're going to solve or find what the rate constant is. Typically, you are given the rate and you are given the concentrations. So in these problems, you're usually given the concentration of the reactants, so some reactants concentration, and you're given the rates that happen. If the other thing you could be given is you could be given a graph, but we're not going to talk about the graph today. So again, you got to find X, find Y, find K. Those are what you're going to solve for. And then you'll be given the reactants concentrations. You'll be given the rate, and you might even be given a graph. And then last but not least, what is the rate constant? It's this lowercase k, and it's some numerical value, and then this is tricky, and some units, but they do not stay constant for the reaction. So what I tell students is the rate constant is the least constant in chemistry, meaning not only will the value change, the units of it are not the same, and it's going to be different. I'm going to put a couple little key points. It's only for a reaction, meaning the one that we have right now, at a temperature, or one temperature, and it's also the units have to be what's called derived or solved for. So it's a constant, yes, but it's constant for only, I'm just going to put the word one instead. It's only constant for that one reaction at that one temperature that we're running our reaction at, and the units are derived after we're done with the experiment. All right, so there's kind of a lot of very new things to do with rate laws. So we have our example. This is just going to be our example problem, our example reaction. I picked nitrogen dioxide because we did that the other day. So for nitrogen dioxide, I'm just going to draw the molecule really quickly. It's got your nitrogen in the center, and then I'm not going to show the bonds. It's a bent molecule like that. And then our carbon dioxide is just one carbon and one oxygen. That would be a linear molecule. So these two molecules are going to slam into each other and then create what we hope is carbon dioxide, which is two oxygens with a carbon in the middle. And they would be two double bonds, but we're not going to worry about that. And then what would happen is one of the nitrogens, is left with one of the oxygens. So as those molecules collide and you let them run into each other with the correct orientation and the correct energy to break bonds, hopefully we'll be able to run a reaction, and then these are the 4 trials that somebody else did. So some other scientist decided trial 1, 2, 3, and 4. They decided to run the concentration at 0.1 and 0.1, and then this was the rate. So we know the rate was 0.0021, what's called molarity per second. So I'm going to talk about that over here. So what is M per second? It's moles of the substance per liter that it's in per second of the reaction. So that's what that means when they have molarity / second, is it's a concentration of your particles per time. So what they're just saying is that's the rate from that graph that we had the other day. That's the rate that occurred of change. So it is a derivative. So that's the rate of change. And then that's how much was created in that, time frame, in this case, seconds. Be careful. The units are typically molarity per second, but they don't have to be. Another little disclaimer is, could the units be something different for rate? Sure. They could actually be particles or molecules per centimeter cubed per minute. So be careful. I'm just going to put this in like a box instead. The units of rate can be any amount, so mole or molecule, over any volume, so liter or centimeter cubed, and then per time. So for the units for rate, when you say something has a rate, those units have to be an amount and a volume and a time. So watch your units of rate, because the AP test or AP test raters might not have them in just moles per second. Okay, so that's sort of our beginning of it. What I'm going to do right now is show you how to derive X and Y first in this video, and then I'm going to do a separate video where we find what is the rate constant. Okay, so the first thing is, how am I supposed to take this data table, and how am I supposed to find what's called the rate law? So my hope again is to find rate. I have that. I'm not going to solve for K, but how am I going to find, and I'll just put question mark, this right there, that X, and how am I going to find the Y, okay? So change that. So that's the point of the first part of this video, is how do we solve for those exponents? So how does this table allow us to do this? And then those are called, the X and the Y, I'm going to go back up here, those are called orders. And then the other thing that's new is there is going to be something called an overall order. So X and Y are called the order of that reactant or reaction. And then if you take and you add X plus Y, so if you take, let me put it over here. So if I take my two question marks, so I'm trying to solve for what is X, and I'm also trying to solve for what is Y. But if I take X plus Y later on, it's going to be called the overall order of the reaction. And that's going to help us with the units and value of K. All right, so how are we going to solve for this? So in the book, I'm going to do the alternative method, but I would highly recommend that you, I'm just going to get rid of that. I would highly recommend that you do not use the method I'm showing you because it's slower, but for the first time around, I will, okay? You want to use what I call the intuitive method the second time around. Okay, so what we're going to do is we're going to pick, I'm just going to take this and sneak this somewhere else here. Let's just sneak it up here. There. So what we want to do is find the question mark, which would be X or Y. But I'm going to solve one at a time. So what I'm going to do is look at my experiment and say to myself, well, which two trials should I compare? So let's say right now I'm trying to solve for the X, okay? And I don't care really what this other one is, this Y. I want to pick two trials where the carbon monoxide stays constant, but the NO2 changes. And the answer is trial 1 and 2 are a good example for that. So for trial 1 and trial 2, I'm going to compare these two, and that should help me find X. Now, how is it going to find X? I'll show you. But if I pick trial 1 and 2, my carbon monoxide stayed the same, okay? And then my NO2 was doubled. So kind of like the game that you were playing with FET, you're putting more molecules of just this one in it, and you're going to keep the number of molecules of that the same. And we already know what happened to the rate. It tells us. We just have to figure out how does that tell us what the X is, this order of that reactant. All right, so what you're going to do is I always take the bigger over the smaller. So what I mean by that is I'm going to compare the rate of trial 2 compared to the rate of trial 1. What that's going to be is 0.0082 compared to 0.0021. I'm hoping that you can already see that that's 4. So the rate went 4 times as fast. But we're also going to put in then K. So we're going to I'm going to take these 2 rate laws and put them over the top of each other like a fraction. And then I'm going to put the numbers in there. So this was 0.2 to some x. And then this was 0.1 to some x. And then the carbon monoxide was 0.1 to the y. And again, 0.1 to the y. They kept that one constant. Now what we're going to do then is sort of like as a fraction. We've done this with even, I think, PV-nRT. You can compare 2 pressure, volume, temperature, moles comparisons and see what's changing. So the first thing is that the rate is 4 times as fast, the 0.0082. So if you want, you can even put that like here if you want to line it up. And then the next thing is I'm just going to show you the K's are going to be, I would say the word would be canceled, yep. And then these are also going to be, whatever Y is, it doesn't matter. Brackets a little strange there. I'm being picky now since I'm recording this. Whatever Y is, they're going to be the same thing. So this ends up being canceled also. So what you have left is just 0.2 divided by 0.1. And then you can put those 2 quantities together, raised to the power of x. And then it just turns into a pretty easy math problem, which is that 4 is going to equal 2 to some x. So then what's the only way x would make this basic math problem work is if x was equal to 2, would that equal 4? So if I take 2 squared, that would, put a little happy face, that would work, right? What that means then is x is 2. So if you go back up here, that's just us saying, okay, well, if I doubled the concentration of nitrogen dioxide, the rate went 4 times as fast. So it has to have like what's called a squaring effect. So that means x is 2, and that's going to be called second order with respect, sounds kind of weird, to NO2. So that would be like in words what they would say is the word answer, is that it's second order with respect to the nitrogen dioxide. Meaning if you change it, think of the game, you got a 4 times the reaction rate compared to just no change or like a double. All right. Then we're just going to do this all over again to find y. But it's more of like which trials should I pick? So of these trials that are sitting here, which trial should I pick for finding out how carbon monoxide changes it, which means we want the nitrogen dioxide to stay the same. And the best answer for that, in my opinion, is comparing trials 2 and 3. Okay, so I'm going to start this all over again. Actually, I think what I'm going to do is I'm going to slide. I'm not going to get rid of this. I'm just going to slide this sort of down out of the way here. But I'm just going to repeat this process again. I just want to make sure you can see the table. I'm going to repeat the process again. I'm going to compare trial 3 and 4. So they ran the experiment 4 times. But I'm going to say, let's do trial 3. So we're going to use trial 3 kind of versus trial 2. So I'm just going to do the same thing that I'm going to compare the rate of how trial 3 went compared to the rate of trial 2 went. This is the long way. And we're going to say it went 0.0083 over 0.0082. That's pretty much just 1, okay? So this is going to be pretty much, not exactly, but pretty much 1. They wanted to have a little bit of air in the lab. And then you're going to compare again the rate constants, and then NO2, and then CO. And then we know the numbers. So instead of putting those 2 things, just trying to kind of show you quickly here. We're going to have the 0.2. And now we know it is squared. But then it doesn't really matter because it would have been removed from the equation anyway. And then 0.2 and then 0.1 to the y. When you're done here, you got 0.2 over 0.1 to y, which means 1 is going to equal 2 to the y. The only way this is going to work is if y is 0, because will that make the equation equal 1? And yes. So then you're going to say with CO, y is equal to 0 because it's a 0 order. So then back up here, we're going to erase this and put a 0. All right, I'll make a separate video for how to solve for the rate, but right now we've answered one part of this question, which is to find the orders of the reactions with respect to each reactant.